Okay, namaste. In the previous session, we have gone through the classification of windmills. Windmills are classified into two categories based on the axis of rotation of the blades of the turbine, such as horizontal axis wind turbine and vertical axis wind turbine. We have gone through the horizontal axis wind turbine in the previous session. In this session, we will be looking on to the vertical axis wind turbine. This is called as vertical axis wind turbine because the axis of rotation of the blades are perpendicular to the ground. That is why it is called as a vertical axis wind turbine. Let us look on to the various parts of vertical axis wind turbine. If you look on to the sketch, it consists of the vertical shaft. To the shaft, blades are attached. At the top and bottom, we have bearings which supports the shaft to rotate, and the shaft is guided by guy ropes on either side. Next thing is support structure. Inside the support structure, we have power generating elements such as brakes, gearbox, generator, and then switch gear control mechanism as well as grid connection. So now let us look on to the main components of the vertical axis wind turbine. We are looking on to three main components. First one is tower or rotor shaft. Here rotor shaft itself is called as the tower. The second thing is blades, and the third one is support structure. Very first one is rotor shaft or tower. If you look on to the tower, it is a vertical tower and it is hollow in nature, and this is rotating in between bearings at top as well as the bottom. These two bearings are going to support the rotation of the shaft. Usually at the top, the shaft is guided by guy ropes, and height of this is usually about 100 meters. So this is what is regarding the rotor shaft or tower. Next is blades. If you look on to the blades, blades are attached to the shaft, and these blades are of aerofoil cross section. If you look on to the sketch, it is very clear that the diameter of the blade is usually less than that of the height of the tower or rotor shaft in case of vertical axis wind turbine. And the last thing is a support structure. This is the support structure to us, inside which we have many power generating components such as gearbox, generator, switch control mechanism, and along with that grid connection. So this is what regarding main components of vertical axis wind turbine. Now if you look on to the working principle, as soon as the wind strikes the blades of the turbine, the blade starts to rotate. Once blade starts to rotate, the shaft attached to the blades also starts to rotate in between the bearing. This shaft is attached to the gearbox in order to speed up its rotation, and then it is provided inside the generator. Once the rotation happens inside the generator, the magnetic flux breaks over there. That leads to the movement of the electrons. That movement of the electrons is termed as the current. This variation in the charges with respect to the time is called as the power. This power will be taken out to the grids through the power cable. So this is what is a working principle of vertical axis wind turbine. In vertical axis wind turbine, we have few of the advantages over the horizontal axis wind turbine. If you look on to few of the advantages, very first thing is we don't need the yaw control mechanism. In case of horizontal axis wind turbine, in order to adjust the blades to the wind, we need a yaw control mechanism. Here the blades are supported in such a way that it can extract the energy from whatever direction of the wind. That is why yaw control mechanism is eliminated over here. Next thing is heavy nozzle. In case of horizontal axis wind turbine, we have provided the nozzle at the top of the tower wherein power generating elements are present. Here the entire power generating elements are present at the ground itself. So because of that, heavy nozzle which has to be placed at the top is eliminated. So because of this elimination, it is easier in design and installation when compared to that of horizontal axis wind turbine. Along with that, since most of the power generating components are present at the ground level itself, maintenance as well as inspection becomes very easier. These are the few advantages of vertical axis wind turbine when compared to that of horizontal axis wind turbine. Yes. Okay, let us look on to the power output from the wind turbine. In order to look on to the power output, generally we used to take a horizontal axis wind turbine into consideration. Before looking on to any terminologies, let us look on to the power that is actually available in the wind. I will call that power available in the wind as a P total. In order to look on to this P total, I will look on to mass flow rate of the wind first. Mass flow rate of the wind is given by rho A V, where rho is the density of the fluid, wind, A area of the blade on which it is striking, velocity of the wind. So, rho A V will be in terms of kg per second. I know the moving air, wind, possesses kinetic energy. Kinetic energy is given by half mv square, where m is the mass flow rate or mass of the wind and v is the velocity of the wind. Here if I substitute m as m dot, this becomes the rate, change in kinetic energy, the rate of change of kinetic energy, that becomes power if I replace m by m dot. So, now I am replacing m by m dot, where m dot is rho A V. So, now finally this equation becomes rho A V cube divided by 2. So, this is the actual power that is available in the wind. So, this is the base to us in order to look into the maximum power output from the turbine. So, already I have said we have taken horizontal axis wind turbine into consideration. This portion is considered as the turbine wheel. To this portion's left side, I have a upstream of the turbine wheel and the right side is downstream of the turbine wheel. Upstream of turbine wheel, downstream of turbine wheel. So, the graph which is above is for pressure variation of the wind, the graph which is below is velocity variation of the wind. So, now at the base point we have Pi. Pi stands for pressure at the inlet, pressure at the upstream of the windmill. Pi and then Pa is the pressure at the windmill, upstream of the windmill, and pressure at the other end of the windmill, and Pe is the pressure of the wind at the exit. In the similar fashion, velocity at the upstream of the windmill, Vi, Va and Vb are the variation in the velocity upon the wind strikes the blades of the turbine, and Ve is the velocity at the exit of the windmill or turbine wheel. So, these are the notations with respect to the curve. That is what I have written over here. AB stands for turbine wheel, Vi velocity at upstream of the turbine, Pi pressure at the upstream of the turbine, Ve velocity at the downstream of the turbine, Pe pressure at the downstream of the turbine. One thing is for very sure, velocity at the upstream of the turbine wheel, Vi, is very higher because wind is striking the blades of the turbine with certain velocity. As soon as it strikes the blades of the turbine, its velocity should come down because the kinetic energy has been extracted by the blades of the wind turbine. And then if you look on to the Ve, the velocity with which the wind is leaving the turbine blades is less. That is what is this condition. Ve velocity at the exit is less than velocity at that of inlet. This is what is the extraction of kinetic energy. Because of that we have this condition over here. Okay, let us go through the derivation part now. Please look on to the section again. This is the upstream to the wind wheel, this is the wind wheel or turbine wheel, and this is the downstream. Now I have taken the section over here, upstream section, the section between I and A. That section has been considered as the thermodynamic system, so that I can apply certain thermodynamic equations. I have SFE for the control volume, steady flow energy equation for the control volume for the section IA. Left hand side is for the inlet section, I mean I section, right hand side is for the outlet section, end portion, that is A section. Here the equation terms are Z is nothing but the potential energy, kinetic energy V square by 2G, U internal energy, PV flow work, Q heat transfer. Again Z at the outlet portion, which is nothing but potential energy, it is nothing but the kinetic energy at the outlet portion, internal energy at the outlet portion, PV flow work at the outlet portion, and W is nothing but the work transfer. Yes. Here there is no change in the potential energy from inlet to outlet, there is no change in the internal energy from inlet to outlet, and there is no heat transfer which is happening, and there is no work transfer which is happening in the section what I have considered, which is nothing but the upstream section. So I will be remained with Pi Vi plus kinetic energy. This is nothing but the flow work because the wind is blowing towards the windmill or turbine wheel, that is flow work, and the kinetic energy at the inlet portion and at the outlet section, which is nothing but flow work and kinetic energy. Now if I alter the equation, Pi I kept it as it is, V is nothing but the volume, especially specific volume, 1 by rho is nothing but the specific volume. So Pi by rho I have kept this term as it is, kinetic energy, and again here also Va specific volume at the outlet section, 1 by rho A is nothing but Va, I have substituted that over here. So now if I multiply the entire section by rho, which is nothing but the density of the air is not changing. So if I multiply this equation by the rho, this rho will get cancelled up with the multiplied rho, and here one more rho comes into picture, and this rho get cancelled with the multiplied rho, and one more rho will comes into picture over here. So this is the one form of equation I have got for the upstream. And similarly, if I look on to the downstream, what is the section for the downstream? It is B and E, the section between B and E, that is what is the downstream section. By considering that also as the control volume, I can apply steady flow energy equation. Upon the application of the steady flow energy equation, I will get the same equation as what I have got for the upstream section. So Pb plus rho Vb square by 2G, which is equal to Pe plus rho Ve square by 2G. If you look on to both the equations are of same fashion. So now if you look on to the conditions, what I need to look on, Vi is greater than Va and Vb is greater than Va. V stands for velocity over there. Please look on to this. This is the upstream section. Before wind strikes the blades of the turbine, Vi is very higher. As it approaches towards the blades of the turbine, the velocity reduces, not in a rapid fashion. Once it strikes the blades of the turbine, the velocity has to be converted into work. I mean the energy has to be extracted. Because of that there is a obstruction, I mean rapid downwards is there in the curve at this portion. Rapid change in the velocity because of extraction of the power which is available in the wind. Again it is not going to be rapid change, it is gradually going to decrease at the outlet portion. If you look on to the condition, Vi is greater than Va and Vb is greater than Ve. V is nothing but the exit velocity, I mean velocity of the wind at the exit of the turbine. In the same fashion, if you look on to the pressure curve is here. If you look on to the pressure Pa, which is higher when compared to that of the Pi, because as soon as the wind move towards the turbine wheel, the pressure starts to build up. In the same fashion, if you look on to the Pe, which is greater than Pb, because once the air is leaving the turbine wheel, its pressure actually rises up to the atmosphere. I mean at the initial stage Pi and at the end stage Pe, we need to have the same pressure, that is nothing but the atmospheric pressure. Pressure variation will be rapid when wind strikes the blades of the turbine. So that is what is the condition I have written over there. Vi is greater than Va and Vb is greater than Ve. Pa is greater than Pi and Pe is greater than Pb. Okay, from the previous expressions we have the upstream equation for the wind blades
Pi plus rho Vi square by 2G, which is equal to Pa plus rho Va square by 2G. In the same fashion, for the downstream section, we have Pb plus rho Vb square by 2G, which is equal to Pe plus rho Ve square by 2G. I have solved this equation for Pa. So, I have sent this term onto the left hand side. I have got this equation, and this equation has been solved for Pb. I have sent this to the right hand side. So, I have got this. Next thing is I have considered Pa minus Pb, because the variation in the pressure on the blades of the turbine is what is going to rotate the blades of the turbine. Because of that, I have considered Pa minus Pb. That means Pb has to be subtracted from Pa. Pa minus Pb will be equal to this minus this section, and here we need to look on to few of the conditions. Very first thing is, if we look on to the sketch, pressure at the inlet section, I mean at the upstream section, and the pressure at the downstream section is almost same. I mean it is a atmospheric pressure. So, because of that, Pe which is equal to Pi which is equal to P atmospheric. I mean all these terms are same. And if I look on to the velocity, Va is almost equal to Vb, which is almost equal to Vt. This condition is because we know compared to the length of the blade, the width of the blade is very small. The variation of the velocity along the width of the blade is very small when compared to that of the variation along the length of the blade. Since the term AB represents the width of the blade, Va is almost equal to Vb, and that is what is equal to velocity of the blades of the turbine. So, because of that, I have considered this assumption also. These two assumptions are dumped into the above equation now. So, Pe and Pi will get cancelled off, and Va and Vb, Va and Vb. If I look on to Va, here it is a negative. If I look on to Vb, negative of negative will become positive. Those two terms will get cancelled off. So, I will be remained with Pa minus Pb, which is equal to rho Vi square minus Ve square divided by 2G. So, this is what is the pressure difference which is causing the rotation of the blades of the turbine. Next thing is I will consider the axial force which is acting on the blades of the turbine. We know the basic equation for the force is pressure into area. Pressure in the axial direction is variation in the pressure along the width of the blade of the turbine into the area on which the wind is striking. Now, we have Pa minus Pb from the previous expression. I have substituted Pa minus Pb over here, and area I have kept as it is, and I have called this equation as number 2. And this axial force is also equal to the change in the momentum of the wind. That is, we know force is mass into acceleration. Force, which is nothing but the axial force. Here I have considered mass flow rate with respect to the acceleration, which is nothing but variation in the velocity, which is V divided by gravitational force. So, now mass flow rate is rho into A into velocity of the turbine, and V is the actual velocity of the wind. Here V is nothing but Vi minus Ve. Vi stands for velocity of the wind before it strikes the turbine, I mean at the upstream section. Ve is the velocity of the wind at the downstream section. So, overall velocity will become Vi minus Ve. I have substituted these two into this equation. So, axial force, I mean change in the momentum of the wind, will become rho A Vt. This is nothing but mass flow rate divided by this G, and this V is given by difference between the velocity at the upstream and the downstream. So, we have two equations now for the axial force. One is this number 2, and the another one is number 3. On the both equations on left hand side we have Fx. Because of that, I am equating equation number 2 and 3. If I equate 2 and 3, on either side we have density of the wind, which is assumed as constant, which will get cancelled off, and area on which the wind is striking, on either side it is same, which will also goes off, and Vi square minus Ve square is splitted as Vi plus Ve and Vi minus Ve. I have kept it as it is, and divided by 2. G goes off on either side, I have remained with Vt and Vi minus Ve. In the next stage, I have cancelled Vi minus Ve with Vi minus Ve. I will be remained with Vt is equal to Vi plus Ve divided by 2. If I look onto the terms, Vt is the velocity of the turbine, which is equal to velocity at the upstream section plus velocity at the downstream section divided by 2. I mean half of the velocities at upstream section and the downstream section will be equal to the velocity of the turbine. I have called that as equation number 4.
Yes.
Okay. Now consider the entire section bounded by I and E, in the sense upstream section, blade width and the downstream section. That is what is the section bounded by I and E as a thermodynamic system, and apply steady flow energy equation to that entire system. We know upon applying the steady flow energy equation, we have already applied this equation for segregated sections. By looking onto that, we will be left out with work done by the air or work done from the wind blade will be equal to kinetic energy that is entering into the blade and kinetic energy of the wind which is leaving the blade, change in the kinetic energy, which is given by Vi square minus Ve square divided by 2G. This is what we will be left out with upon applying steady flow energy equation to the section I and E. I have called that as equation number 5. And then if I want to get the power, I have got work done by the air or work done from the wind turbine. If I multiply the change in the mass of the air, so power will be obtained. So power is mass flow rate multiplied by the change in the kinetic energy, which is nothing but the work done. Mass flow rate into work done will give you the power. We have already got mass flow rate as rho A Vt, where rho is the density, A is the area, Vt is the turbine velocity, and change in the kinetic energy. Again, in the from the previous expression, we have got Vt as average kinetic energy at the inlet and at the outlet. So rho A Vi plus Ve divided by 2 times of change in the kinetic energy. If I multiply these two, then I will get 4G. So that is what is this 4G. Then I will be remained with this equation. In this equation, if I consider Vt, turbine velocity, as the inlet airstream velocity and exit velocity of the air as 0. Please substitute Vi as Vt over here and Ve as 0. Then I will be obtaining the power available in the wind. This equation we have looked on to in the previous discussion itself. So Vt equals Vi and Ve is equal to 0 will lead us to the power that is actually available in the wind. But Ve, that is the velocity of the air or velocity of the wind while leaving the turbine blade, cannot be equal to 0. If velocity is 0, that means all the wind has to accumulate at the end section, I mean at the outlet portion. That is not possible. And if you look on to the Ve in the equation, in one term Ve is negative and in the other term Ve is positive. Too high or too low values of Ve abruptly changes the power developed by the wind turbine. So because of that, Ve plays a huge role. Then optimum Ve is going to give us the maximum power output from the turbine. So if you want maximum power output, we need to have optimum exit velocity, optimum wind exit velocity. What we have to do is, this equation has to be differentiated with respect to optimum Ve, and then it has to be equal to, and it has to be equated to 0. So dP divided by dVe, I mean this power has to be differentiated with respect to the optimum Ve, and then it has to be equated to 0. So dP divided by dVe, which is equal to rho A by 4G, all these things are constant and the variables are velocity terms. Those velocities are differentiated with respect to the velocity, I mean exit velocity of the wind. So dP divided by dVe will be equal to this much, and then it will be equal to equated to 0. So I have got finally this equation. Vi square minus 3 Vi square minus 2 Vi into Ve, which is equal to 0. I have ended up with the quadratic equation. Now I need to solve this equation to get the optimum Ve. Upon solving this equation, I have got two solutions for it. One is Ve can be equal to Vi, or Ve can be equal to 1/3 of that of Vi. If you look onto the solutions, Ve is equal to Vi. This Ve is equal to Vi is not at all possible, because velocity of the wind at the exit of the blade will not be equal to velocity of the wind before it strikes the blades of the turbine. So this possibility is eliminated. I have remained with only one possibility, which is nothing but Ve is equal to 1/3 of that of Vi. That means Vi divided by 3. So this is the optimum exit velocity, which is going to result as the maximum power by the wind turbine. Now we have got the optimum velocity, optimum exit velocity, which is nothing but 1/3 of that of inlet velocity of the wind. Now I will substitute this optimum velocity in the power equation. I have the power equation with me. Now Ve should be 1/3 of that of Vi. As soon as I substitute Ve as 1/3 of that of Vi, power becomes power maximum. So 1/4G rho A Vi, I have kept it as it is. So Ve is nothing but Ve optimum now, which is 1/3 of that of Vi. Vi square minus 1/3 Vi whole square. Solve the equation. Take the LCM over here. 3Vi plus Vi divided by 3. Now it is 1/3 whole square. 1/3 whole square is 1/9 Vi square. 9 is the LCM. 9 Vi square minus Vi square divided by 9. Solve the equation now. 4 goes off, and then I will be remained with 8. This 8 divided by 27. 9 into 3 is 27 divided by G rho A Vi into Vi square is Vi cube. So this is what is the final expression for maximum power output from the given wind turbine. I have altered the equation over here. I have the equation as 8/27G rho A Vi cube. What I have done is I have changed the numerator into 16, and I have divided 16 by 2. 16 by 2 again gives me the same value, which is nothing but 8. So 16 by 2 is 8. 8 divided by 27 G rho A Vi cube. It is the same equation, but I have changed the numerator into 16 and divided that numerator by 2. Now this is the initial expression what we have seen into, that is nothing but the total power that is available in the wind, which is nothing but half G rho A Vi cube. On the left hand side I have power maximum, in the sense maximum power that is developed by the turbine. On the right hand side, if I solve the numerators, I will get the constant, which is 0.593, and the remaining thing is total power that is actually available in the wind. If you look onto the equation, the maximum power developed by the turbine is 0.593 times of that of actual power that is available in the wind. So that is what is the expression to us. If I alter the equation again, power max I will kept as it is, and then I will take the power total onto the left hand side. Power max by power total will be equal to 0.593, which is usually termed as Cp, where Cp is coefficient of performance for the given windmill or wind turbine. If you look onto the Cp, Cp is nothing but power output from the given wind turbine to the actual power that is available in the wind. This ratio will give us the coefficient of performance of the given wind turbine. It is very clear the denominator is always greater, because this is the actual power available in the wind. All the power cannot be extracted. That is what is there in the numerator. Actual power output from the turbine, which is always less than that of the actual power which is available in the wind. So that is what is called as the coefficient of performance for the given wind turbine. We have derived the equation by considering the horizontal axis wind turbine. So now it is very clear that for horizontal axis wind turbine, Cp coefficient of performance cannot be exceeding the value of 0.593. Wherever I have to calculate the maximum power that is available, that can be produced by the turbine, I will be making use of this if I know the value of actual power that is available in the wind, or else I will be making use of this equation to calculate the overall power developed by the turbine. Okay, lastly we need to look on to the problems that are associated in generating the power from the wind. Very first one is noise production. We knew huge blades needs to be needed in order to extract the power from the wind. As soon as the air strikes the blades of the turbine, it is going to disrupt the movement of the wind. So this is going to generate the huge noise. This has to be taken care while mounting the wind turbines. That is the major disadvantage in mounting the wind turbines. Second one is visual impact. Since huge columns are needed as well as huge blades are needed, that is going to affect the visionaries, I mean visuals of the nature. That is the second one. And the next thing is, since blades are rotating at a very high speed when the wind velocity is very high, that may affect the wildlife, especially birds as well as bats during the night session. Recent surveys also says many bats as well as birds have died because of the mounting of wind turbines. And the last one is, in order to mount the wind turbines, we need to survey. Most of the surveys says forest areas are the better areas to look onto to mount the wind turbines. So deforestation has become a major issue in extracting the power from the wind. So these are the few problems that needs to be looked onto while extracting the power from the wind. So that is what is for the today's session. We will meet in the next session.